So by the turn of the 20th century, they worked out that light was a transverse wave that consisted of electric and magnetic fields that are oscillating, okay? And they were pretty sure they knew what light was. However, some new information came up based on spark distances, actually, when how far a spark would jump in air. It turned out that if light shone on metal, you would actually get the spark to go further than without. So they presumed that the light was giving the actual electrons some energy to leave the metal. So this was called the photoelectric effect. So photo means light, and then the electric obviously is producing electrical charge there because it releases electrons. So I won't get into the history of that now, but I just want to show you some key things in an experiment they did to actually analyse this. So the idea was to actually analyse light coming down and electrons being forced to leave it. So if it was a wave, what they felt was that if light shone down is a wavefront here and hit the electrons in there, you would get a whole group coming off there. And if you made the light more intense, you get more electrons and they might be more energetic and so on. Okay, so they wanted to test that out. So you can do an experiment here, similar to what they've done. So there's a few ways you can set this up. Let's just do a simple one here. Let's say you had a wire hoop there. On the other side we have your metal plate that you're going to aim this thing at. Alright, and we're going to shine light through here. But we want to filter the light there to make sure it's one frequency. So you put a filter in there. And it might be a range of frequencies that lets through, but you know the range of frequencies that lets through. So you'll get a certain frequency or range of frequencies coming through there. Goes through the hoop, shines onto this surface here. Okay. Now what will happen then is they found that for certain conditions electrons would leave that surface, head across to the loop here and become part of the circuit there. Alright? And what we want to analyse is what the properties of these electrons are. So there's a few ways you can do that. First of all, you can put a microammeter in there to measure very small currents because the current produced is not very big. So you put a microammeter there and that's part of your circuit there, and that'll tell you how many is going across this gap and flowing around in that circuit there. Okay. Now if you want to measure their energy, you need to put in some sort of a voltage there and a voltmeter to record the energy. So what you would do is you would put in a potential difference here. Now what we want to do is slow these down so we can work out how much energy they started with. So if these are negative coming off here, you make this a negative plate and we make it adjustable as well. Okay. And what we can then do is record the voltage we needed to actually slow these electrons down. So you'd set up an experiment like that, and this would all be done in a vacuum. In a vacuum, so that the air particles don't interfere with it, and you're just going to come off clean. So what they found they would do is they would turn up the voltage on this here, so you increase the voltage on this potentiometer, and as you increase the voltage, they found the current here drops slowly. And the reason for that is we started to turn some of these electrons around. Now what they found happening was as they increased this up, it started to turn more and more around, so the current steadily dropped down. Now that meant that some of them had more energy than others because the ones with low energy were already lost when you first turned this voltage up. And the more you turn the voltage up, the more electrons you lost because the more were turned around. Now eventually you get to a point where the current actually drops to zero. And just as you reach that point, you know you've turned the fastest ones around. So you can measure the ones with the highest kinetic energy as they leave this metal here based on your voltage. So let's say you had a voltage here of 2 volts here that was turning them around. Now you know for a fact then that when they got to here or just missed getting into here, they had a potential energy there of 2 electron volts. Because the work done there in slowing them down to a stop is delta VQ. You could get it in joules, by the way. It'd be 2 times by 1.6 by 10 to the minus 19, which is 3.2 by 10 to the minus 19 joules, or 2 electron volts. So you actually know the energy of the maximum kinetic energy, rather, of the electrons in this situation based on this frequency. Okay, and you can then change the filter and find out for different frequencies what is the voltage here, and plot a graph and start to get a relationship between the maximum energy, or this will give you the maximum energy here in electron volts, versus the frequency. And you get a graph like this, which we'll come back to. Now the results of this were very odd and did not show wave support. And the reason for that was what they found was that if you made the light as intense as you liked, it did not cause a release of electrons if the frequency was too low. So there was a minimum frequency needed for electron emission. No matter how intense you made the light, it did not work unless you got to a minimum frequency. Anything below that did not work. Now that didn't make sense in terms of wave theory, which is not the course, by the way, because a wave front should come down and hit the metal surface there, and eventually, if you have a high enough intensity here, the electrons should build up enough energy and leave. They did not do that. So frequency was definitely an important thing. Okay. Other things to bear in mind was a higher intensity light did not give higher energy electrons. They had no effect at all. So the kinetic energy electrons did not depend on the intensity. It depended on the frequency. All right. So in actual fact, as the frequency went up, you found that the kinetic energy maximum went up as well. All right. Not in proportion, by the way, but did go up. Okay. There was no time delay between the light waves hitting it and the electrons being released. Finally, when you had a higher intensity light, you got more electrons or more current. Okay. Now, there were several ways that this wave theory did not actually support these observations here. This idea of a minimum frequency was not supported by it. The fact that if you had more frequency, light with a higher frequency, the kinetic energy went up. It was theorised that if you had high frequency light, they would be coming down and releasing less energy, okay, because of a resonance property there. There was no time delay. That didn't make sense either, because if you use low intensity light, they figured that after a while you should get release if you're using waves. So if you shoot down low energy waves, there should be a time delay before it actually is released, before the electrons get enough energy to leave the metal surface. So there's a few things that were wrong here. So how can you explain these observations from the wave model? The answer is you can't. So they had to come with another model here, and there was another model going around about photons or lights coming in bundles of energy, which Einstein used to explain this photoelectric effect. Okay.